Okay, today we're looking at section 7.9, conditional probability and the multiplication rule. Understanding how probabilities can shift as we learn new information is critical in the analysis of our second type of compound events. Those built with and. This section will explain how to compute probabilities of those compound events. So we got to consider what's called conditional probability. When we analyze experiments with multiple stages, we often update the probabilities of the possible final outcomes, or the later stages of the experiment based on the results of one or more of the initial stages. These updated probabilities are called conditional probabilities. In other words, if O is a possible outcome of the first stage in a multi-stage experiment, then the probability of an event E conditional on O is denoted the probability of E given O has occurred is the updated probability of E under the assumption that O occurred. So you're about to roll a special six-sided die that has both a colored letter and a colored number on each face. The faces are labeled with the following, and it's the same as the previous. A red one and a blue A red one and a green A, an orange one and a green B, an orange 2 and a red C, a purple 3 and a brown D, and an orange 4 and a blue E. So find the given conditional probabilities. What is the probability that the letter is a vowel given the number is orange? So we need to look at our orange numbers. There's another orange number. Is that all of them? 3? Okay, so we have a total of 3 orange numbers. We know it's orange, so we know it's going to be one of these 3. Are any of the letters a vowel? B is not a vowel. C is not a vowel. But we have a blue E, so we have 1 out of 3. So now that we know that it's an orange, the color of the number is orange, the probability of having a vowel is 1/3. Okay, let's look at our next one here. The letter is I, given the number is red. So I have a red number. I have a red one here. I have a red one here. Oh, the letter, not the number. Be careful doing these. I have a red. Okay. It's easy to get backwards here. I have a red 1. I'm looking at enough red numbers. Red 1. Any more red numbers? There's a red letter. What is the probability the letter is I given the number is 1? I think this is supposed to be an A because there are no I's. So if we change that to A, red 1, blue A, red 1, green A. So if I know the number is red, a red 1, or the number is red, then I know my letter is going to be A. So the probability would be 1. The initial statement, I, there are no I's, so the probability would have been 0. Okay, the probability, the number is 1, or the number is red, given the number is 1. So let's see. Here's a red 1. Here's a red 1. Here's an orange 1. So given that the number is 1, I have 3 number 1s. What is the probability that it's red? Well, 2 of those 3 are red, so it would be 2/3. So if you recall, in trees, tables, and outcomes, we introduced the concept of dependence between stages of a multi-stage experiment. We stated at the time the two stages were dependent if the result of one stage affects the other stage. We explained the dependence in terms of sample space. Sometimes that dependence can be a little more subtle. It's more properly understood in terms of conditional probabilities. Two stages of an experiment are dependent if the probability of E given F occurs does not equal the probability of E given F prime has occurred, or F complement has occurred, or some outcome of second stage E and outcome of first stage F. Now let's look at some more compound events using and in the multiplication rule. So for multi-stage experiments, the outcomes of the experiment as a whole are often stated in terms of the outcomes of the individual stages. Commonly, those statements are joined with and. For example, in the sock drawer example, so this brings us to our multiplication rule for probability. If E and F are events associated with the first and second stages of an experiment, then the probability of E and F is equal to the probability of E times the probability of F given E has occurred. So in the addition rule for probability, we consider probabilities of events connected with and in the statement of the inclusion-exclusion principle. These two scenarios are different. In the statement of the inclusion-exclusion principle, the events connected with and are both events associated with the same single-stage experiment on the same stage of a multi-stage experiment. In the multiplication rule, we're looking at events associated with different stages of a multi-stage experiment. So let's see how this works. You're drawing two cards in order from a deck containing only the cards Ace of Hearts, Ace of Clubs, King of Spades, 10 of Hearts, 9 of Hearts, 9 of Spades, 9 of Diamonds, and the 6 of Clubs. Compute the following. Draw a heart first. So what's the probability of getting a heart? How many hearts do I have? 1, 2, 3. 3 hearts. How many cards do I have? 1, 2, 3, 4, 5, 6, 7, 8 cards. The probability of getting a heart is 3 over 8. And what is the probability of getting a spade given that I have taken a heart? Well, how many spades are there? 1, 2. Now, since I've pulled a heart out, how many cards are left? 7. So we have 6 over 56, which is 3 over 28. Okay. Look at this next one here. What is the probability if we draw a 9 first? So there's 1, 2, 3 9s. The probability of drawing a 9 is 3 out of 8. And a 6 second. Now there's 1 6. And there's 7 cards left now. So we have 3 over 56. And what's the probability we draw 2 hearts? Well, how many hearts were there? 1, 2, 3. So probability first card is a heart is 3 over 8. Probability the second card is a heart given the first card was a heart would be 2 over 7, which would be that 6 over 56 again, or 3/28. Okay, so you're about to perform the following two-stage experiment. First, you will flip a coin. If the result is heads, you roll a standard 6-sided die. If the result of the coin flip is tails, you roll a modified 6-sided die with faces labeled 1, 1, 1, 2, 2, 3. Use a tree diagram to find the probability of rolling each of the numbers from 1 to 6. Okay, so I flip a coin. I have heads or I have tails. Now, if I have heads, roll a standard 6-sided die. 1, 2, 3, 4, 5, 6. So I roll tails. I have 1, 1, 1, 2, 2, 3. Okay? So I have a total of 12 possibilities. So the size of my sample space is 12. Okay, so what is the size of this sample space where the outcome is 1? 1, 2, 3, 4. What is the size of the sample space where the outcome is 2? 1, 2, 3. And the sample space is 3. 1, 2. And then 4, 5, and 6. And just 1 each. So if a roll is 1, 2, 3, 4, 5, or 6, what is the probability? So there's a total of 12 outcomes. So 4 of them could be 1, so that would be 4 over 12, or 1/3. 3 of them could be 2, so that would be 3 out of 12, or 1/4. 2 of them could be 3, so that'd be 2 out of 12, or 1/6. And then the rest of these would be 1 over 12. And that finishes up section 7-9.